Discussion about logarithmic functions and equations. And in this segment, we are going to be talking about how do we solve logarithmic equations using the definition of a logarithm. So, if we're using the definition of a logarithm, it probably makes sense for us to recall what that is. What is a logarithm? So remember that when we introduced the idea of a logarithm, we said that this equation, log base b of y equals x, can be rewritten in exponential form. Remember, we said we can get rid of the log by writing this as b raised to the x is equal to y. Now, there are some restrictions here, but that is the general idea. We can take things and rewrite them in exponential or logarithmic form, depending on what we have. So that comes in handy if we have an equation that can be written in the form of a single logarithm is equal to a constant. If you have a logarithmic equation and there is a constant somewhere in it, then you can probably manipulate the equation so that it is 1 log is equal to that constant. Or if you're presented with an equation that has more than one logarithms and there is a constant, well, then that means that there's probably more than one logarithm on a specific side. We want to take those logs and condense them into a single logarithm before we move forward. Now, one thing you have to remember when you are solving logarithmic equations is you must always check your answer in the original equation and make sure that your solution generates a positive argument. That means we are going to reject any solution that generates a non-positive argument. All that means is we're going to substitute our answer back in and make sure that I'm not trying to take a log of something that's not positive, either negative or 0, because in that case, we would want to reject that solution. Okay, so here are 3 examples of logarithmic equations that we can solve using the definition of a logarithm. And so what we want to see happen is we want to manipulate the equation so that I have a single log on one side of the equation and a constant on the other. And with this first example, I have log base 3 of the quantity x minus 5 is equal to 4. So on the left-hand side, I have a single log, and on the right-hand side, I have a constant. That's perfect. If it's in that form, then I can go ahead and rewrite it as an exponential equation. I can say, well, that's the same as 3 raised to the 4th is equal to x minus 5. And then I can go ahead and solve for x. I can move the 5 to the other side by adding 5, and I'd have 3 to the 4th plus 5 is equal to x, which means x is equal to 86. Okay, so I've solved through, and then I want to make sure that I verify that I'm not getting anything that's not positive out when I take that 86 and sub it back in. And this is nothing really new. We always want to check our work, so let's go ahead and sub that in. Log base 3 of the quantity 86 minus 5, is that equal to 4? Well, 86 minus 5 is 81. So we've got log base 3 of 81. Is that equal to 4? Well, since 3 to the 4th is 81, we indeed have a good answer. All right, for this next example, notice I have a single log. I have a constant on the other side, but this log is not alone. Okay, we want to get rid of this 2 before I move on into rewriting it. So let's move this 2 to the other side, and when we do that, look, I have a single log, and that's equal to a constant. Once we have it in that form, I can rewrite that in exponential form. So do you remember what the base of this log is? The base of just log is 10, right? So 10 squared is equal to x. Oh, that's a piece of cake. That means x is equal to 100. All right, so let's go ahead and sub it in, make sure that we're all good. Is log of 100 minus 2 equal to 0? Well, 10 squared is 100, so that's 2 minus 2, and that is equal to 0, so we are good. All right, next example, we have ln of the quantity 2x minus 1 is equal to 0. Notice this equation is already in the form that we want it to be in. I have a single log on one side and a constant on the other. So I can go ahead and rewrite this in exponential form, remembering that the log of the natural log is e. So I can say that e to the 0 is equal to 2x minus 1. And I know that e to the 0 is the same as 1. So 1 is equal to 2x minus 1. And if I bring that 1 to the left-hand side, I've got 1 plus 1 is 2x. And that means that 2 is equal to 2x. And I can divide out the 2 and say that x is equal to 1. Let's go ahead and double check and make sure that that satisfies our original equation. So the natural log of 2 times 1 minus 1, that's 2 minus 1 is 1, is that equal to 0? Is the natural log of 1 equal to 0? Well, is e to the 0 equal to 1? It surely is, so I'm good to go. Okay, so I have 3 more examples for you, and notice that they're a little more challenging. We started out with some things that were pretty easy, and now we're going to have to do a little manipulation before we actually can write it in exponential form. All right, but let's start with this first one, and I want you to put a box around the logarithm, okay? Just the log. I'm sorry, on the left-hand side, this part, then you'd be correct. So log base 5 of 3x is our logarithm, and it is not isolated. And so I need to isolate it before I can rewrite it in exponential form. So how would I get rid of this 2? I would divide that out. And I can say log base 5 of 3x is equal to 2. Now, since I have a single log and it's equal to a constant, I can rewrite this. I can rewrite it in exponential form and say 5 squared is equal to 3x, and solve for x by saying that x is equal to 25 divided by 3. Now I would definitely want to make sure that I have an answer that satisfies my original equation. And let's see, if I sub that 25 thirds back in, I've got 2 times the log base 5 of 3 times 25 thirds, and I want to know, is that equal to 4? Well, notice right away that 3 times 25 thirds is just 25. So I can say that 2 times log base 5 of 25, is that equal to 4? Well, think about just the log part. Log base 5 of 25. 5 raised to what power is 25? Well, that whole thing becomes 2. So 2 times 2 is equal to 4, and that's a good solution. All right, for the next example, box that log. So you should, on the left-hand side, have just the ln of x box. That means I need to get rid of the 5 that is being added and the 2 that is being multiplied. And you would do that just like if you were just solving for x. If this was 5 plus 2x is equal to 4. You would first subtract a 5, and then you would divide by 2. So let's do that. If I subtract a 5 here, I have 2 times ln of x is equal to negative 1. And then if I divide through the 2, I have ln of x is equal to negative 1/2. And now I'm in the right form. I have a single log on one side and a constant on the other. And so now I can rewrite it in exponential form. And so the base of that natural log is e. So I have e raised to the negative 1/2 is equal to x. And so I've solved my equation. I want to make sure that my solution satisfies my original equation by subbing it in and making sure. And if you see here, if I substitute this e to the negative 1/2 in for my variable, this ln and this e will cancel each other out. So I would have 5 plus 2 times negative 1/2. Is that equal to 4? Well, since 5 plus 2 times negative 1/2 is 5 minus 1, that is equal to 4. And so we have a good solution. Now this last example here If I said box the log, you might have trouble because there are two. And so in this case, we need to condense. We have two logs on that one side of the equation. And I've got a constant on the other, that's great, but those two logs need to be condensed into a single log. And remember, if you're condensing two logs that are separated by a minus sign, then I can take the arguments and divide them. So this would turn into log base 4 of x divided by x minus 1, and that is equal to 1/2. Okay, so I have that single log, and that's equal to a constant. And so now I can rewrite it in exponential form. 4 raised to the 1/2 power is equal to x divided by x minus 1. Okay, well, what is that 1/2 power again? Do you remember? The 1/2 power is the same as the square root. So what is the square root of 4? Let's go ahead and replace that. And we would say 2 is equal to x divided by x minus 1. And then if I multiply both sides of the equation by x minus 1, I would have 2x minus 2 is equal to x. Combine our like terms and solve for x, and we would have x is equal to 2. All right, let's double check and make sure that this actually satisfies our equation. Log base 4 of 2 minus log base 4 of 2 minus 1, is that equal to 1/2? Well, let's look at the first logarithm first. Log base 4 of 2. Well, 2 squared is 4, so 4 to the 1/2 power will be 2. So this part is 1/2. And then let's look at the second log. Log base 4 of 2 minus 1. Well, 2 minus 1 is 1. So log base 4 of 1. Anytime we take the log of 1, no matter what the base, we get a result of 0. So what I really have there is 1/2 minus 0. And that does indeed equal 1/2. So I am good to go here. So remember, if you have a constant in the equation, what we really want to see happen is that equation rewritten so you've got one log on one side of the equation and a constant on the other. And then after you do that, you're going to rewrite it in exponential form, and then you are well on your way to victory. In the next installment, we are going to be looking at a different type of logarithmic equation. And in that case, we will be looking at logarithmic equations that can be solved using the one-to-one property. I will see you then.